In this episode, we focus on assurance, which is the practical art of building justified confidence that a system is actually secure in the ways it claims to be secure. Beginners sometimes hear the word assurance and imagine a stamp of approval or a single assessment event, but security engineering treats assurance as a continuous relationship between claims and evidence. A claim might be that only authorized users can access sensitive records, that changes are controlled, or that a system can resist predictable failures without losing integrity. Evidence is what supports those claims, and assurance methods are the ways we generate, evaluate, and maintain that evidence over time. The challenge, and the reason this topic matters for ISSEP, is that assurance looks different depending on what you are assuring, because software, hardware, virtual environments, and cloud services each have different failure modes and different visibility. The goal is to help you choose assurance methods that fit the system type and the risk, so you can defend security decisions without relying on hope or vague statements. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good foundation is to define assurance methods in a way that stays useful across contexts and does not depend on any one tool. An assurance method is a structured way of collecting and evaluating evidence about security properties, such as confidentiality, integrity, availability, and accountability. Methods can include reviews, analyses, tests, inspections, monitoring, and controlled demonstrations. But the key is that each method produces evidence you can connect back to a requirement or a security claim. If you cannot connect evidence to a claim, you might have activity, but you do not have assurance. Beginners often assume that more testing always equals more assurance. Yet the quality of assurance depends on relevance, coverage, and the ability to repeat the method after changes. A method is also only as valuable as the assumptions behind it, because evidence collected in an unrealistic environment or under unrealistic conditions can create false confidence. When you choose assurance methods well, you reduce blind spots and you make security discussions calmer because decisions are anchored in observable facts rather than opinions. That ability to choose and justify methods is exactly what exam scenarios often try to measure. Before choosing methods, it helps to understand that assurance is always about a specific set of security claims, not about a vague feeling that a system is safe. Claims usually come from security requirements, policies, or risk decisions, and they can be as simple as access must be controlled or as complex as recovery must be possible within a defined time after disruption. The right assurance method depends on what you are trying to prove and how the system could fail. If the claim is about code behavior, methods that examine logic, input handling, and authorization enforcement are likely to matter. If the claim is about hardware integrity, methods that focus on physical tamper resistance, firmware state, and supply chain trust become more important. If the claim is about a cloud service boundary, methods that evaluate shared responsibility, configuration correctness, and provider evidence may dominate. Beginners sometimes try to start with the method, like choosing penetration testing because it sounds strong, but mature assurance starts with the claim and the risk. On the exam, the best answer is often the method that produces the most relevant evidence for the claim under the scenario's constraints. Software assurance tends to revolve around behavior, change, and the gap between what developers intended and what the system actually does when stressed. A strong software assurance approach often combines design review, implementation review, and verification testing to confirm that security requirements are enforced consistently. This includes evidence that authorization checks happen at the right boundaries, that inputs are validated appropriately, and that failure conditions do not produce unsafe outcomes like leaking sensitive data or granting unintended privileges. Beginners sometimes think software assurance is mainly about finding vulnerabilities, but assurance also includes confirming that security properties remain true across updates, which means repeatable checks and traceable evidence. Because software changes frequently, methods that can be applied repeatedly without massive effort are especially valuable, since a one-time deep review can become outdated quickly. Another common misunderstanding is assuming that functional tests cover security implicitly, when security often fails in edge cases, unusual sequences, and error handling paths. Software assurance is strongest when it produces evidence that maps directly to requirements and can be refreshed as the software evolves, so confidence stays aligned with reality. Hardware assurance has a different character because hardware is long-lived, physically instantiated, and often less forgiving when foundational trust is compromised. Assurance methods for hardware frequently start with establishing a chain of trust, meaning you have evidence about where the hardware came from, how it was handled, and what its initial trusted state should be. Because hardware can be physically accessed, methods that include inspection, physical security evaluation, and controlled validation of firmware integrity become important, especially in environments where devices are deployed in exposed or remote locations. Beginners sometimes assume that if software is secure, the system is secure, but a compromised hardware platform can undermine software controls by altering boot behavior, hiding malicious functionality, or exposing secrets stored on the device. Hardware assurance also has a lifecycle aspect, because firmware updates, component replacements, and configuration changes can change the trustworthiness of the platform over time. Evidence often includes baseline configurations, approved update processes, and monitoring signals that detect unexpected changes or tampering. When you select hardware assurance methods, you are often trying to prove that the platform you are building on is trustworthy enough to support the security claims made by the software and the system as a whole. Virtual environments add another layer because virtualization changes what the boundary looks like and changes who controls which parts of the stack. In a virtual system, security claims often depend on the isolation between workloads, the correctness of hypervisor behavior, and the configuration choices that define how resources are shared. Assurance methods here focus on confirming that isolation assumptions are valid, that administrative access to the virtualization layer is controlled, and that the configurations that define networks, storage, and management interfaces are consistent with security requirements. Beginners sometimes assume that virtualization automatically provides strong separation, but misconfiguration or overprivileged management can collapse isolation quickly and turn one compromised workload into a broader compromise. Virtual assurance also benefits from methods that check for drift, because virtual infrastructure can change rapidly as workloads are created, moved, and scaled. Evidence might include configuration baselines, change approval trails, and monitoring that detects unusual management actions or unexpected connections between virtual segments. The central idea is that virtualization can improve security by enabling clean separation and controlled templates, but it can also increase risk if the control plane is not assured. Choosing methods that target control plane integrity and workload isolation is often more defensible than generic tests that do not address the unique failure modes of virtualization. Cloud systems require careful assurance thinking because cloud changes the visibility you have, the evidence you can collect directly, and the responsibilities you must manage. In cloud, many security claims depend on configuration choices made by the customer, on service guarantees made by the provider, and on the interaction between the two, which is why shared responsibility is a practical reality rather than a slogan. Assurance methods in cloud often emphasize configuration assessment, identity and access governance validation, logging and monitoring verification, and careful evaluation of provider documentation and attestations that describe what the provider secures. Beginners sometimes assume cloud is either automatically secure or automatically insecure, but the truth is that cloud can be very secure when configurations are disciplined and monitoring is strong, and it can be very exposed when defaults are permissive and ownership is unclear. Cloud assurance also benefits from continuous methods because cloud resources can be created and changed quickly, making snapshots less reliable as the only evidence. Evidence can include consistent policy enforcement across accounts, validated logging pipelines, and documented mappings between requirements and cloud configurations that implement them. Selecting assurance methods in cloud often means choosing approaches that confirm your configuration choices match your claims and that you can detect drift and misuse promptly. Across all these environments, one of the most important assurance decisions is choosing between methods that are preventive, detective, or confirmatory in their evidence. Some methods, like design review and requirements traceability, create confidence by showing intent is correct and structured. Other methods, like testing and controlled demonstrations, create confidence by showing the system behaves correctly under specific conditions. Still other methods, like monitoring and measurement, create confidence by showing the system continues to behave correctly in the real world after deployment. Beginners sometimes treat one category as superior, such as believing testing is the only real proof, but strong assurance usually combines categories so evidence is layered. If you rely only on early reviews, you risk false confidence because implementation and operations can drift from intent. If you rely only on monitoring, you may detect problems but fail to prevent them from being built in repeatedly. If you rely only on testing, you may confirm certain behaviors but miss slow drift and emergent interactions. A mature choice of assurance methods balances these evidence types so that claims are supported before deployment and remain supported afterward. Another core idea that makes method selection easier is understanding assurance strength, meaning how convincing the evidence is for the claim and how resistant it is to being undermined by change. Stronger assurance does not always mean heavier or slower, but it does mean evidence that is closely tied to requirements, repeatable, and hard to fake. For software, strong assurance may involve consistent verification tied to requirements and controlled change processes that ensure evidence stays current. For hardware, strong assurance may involve baselines and integrity checks that confirm the platform has not deviated from trusted states. For virtual systems, strength often comes from control plane governance and repeatable configuration validation, because the control plane is where broad impact is possible. For cloud, strength often comes from continuous configuration evaluation and validated monitoring coverage, because configuration is the main lever customers control. Beginners sometimes chase the most impressive-sounding method, but impressive is not the same as appropriate, and an inappropriate method can waste time while leaving the real risk untouched. On the exam, a defensible answer often chooses a method that matches the claim and addresses the most likely failure mode rather than choosing a generic method with broad but shallow coverage. It is also useful to understand that assurance methods can fail if they are not aligned with lifecycle and change, because evidence ages quickly in modern systems. A review performed months ago may no longer reflect current behavior if the system has been updated repeatedly, if dependencies changed, or if configuration drift occurred. This is why methods that produce repeatable evidence are so valuable, especially in environments that deliver frequently. Continuous monitoring, CONMON, is often part of this story because it provides ongoing signals that help confirm whether controls are still operating as intended. But monitoring alone is not enough if you do not know what signals matter for your requirements. Beginners sometimes treat monitoring as collecting lots of data, but assurance requires purposeful measurement tied to claims, like monitoring privileged access changes when you claim strong access control, or monitoring unusual data movement when you claim data handling protections. Change control also matters because if changes are not tracked and approved, you cannot know when evidence should be refreshed or which claims might be impacted. Selecting methods without considering change is a common pitfall because it creates assurance that looks strong on paper but is fragile in reality. A mature approach links method selection to the system's change tempo and to the points where drift is most likely. Assurance selection also benefits from recognizing where you have direct evidence and where you must rely on indirect evidence, because not all environments allow the same depth of inspection. In cloud services, you may not be able to inspect the provider's underlying infrastructure, so you rely on provider attestations and service documentation for that part of the claim, while you gather direct evidence for your configurations, identities, and monitoring. In proprietary components, you may have limited visibility into internals, so you rely more on behavioral testing, documented vendor practices, and operational monitoring to detect anomalies. In open components, you may have more opportunity for review, but you still need evidence that the deployed system matches what was reviewed and has not been altered in unsafe ways. Beginners sometimes assume that indirect evidence is always weak, but indirect evidence can be acceptable when it is credible, current, and matched with compensating checks in areas you can control. The key is to be honest about what you can prove directly and what you can only infer, and then choose methods that reduce the risk of those inferences being wrong. Exam scenarios often test this by describing constrained visibility and asking for a realistic assurance approach that still produces defensible confidence. Good answers show you understand the boundary of your evidence and choose methods that strengthen the weakest link. A final set of considerations involves cost, timeliness, and operational fit, because assurance methods must be sustainable or they will be bypassed under pressure. A method that requires rare experts, long delays, or heavy manual effort may be performed once and then quietly abandoned, which creates a dangerous gap between what the organization believes and what it actually knows. Sustainable assurance often uses lighter, repeatable checks paired with targeted deeper assessments where risk is highest, rather than trying to apply maximal rigor everywhere. For beginners, it helps to see this as similar to how you maintain health. You do regular habits that catch problems early, and you do deeper examinations when there is a reason, rather than doing one massive check and then ignoring signs for years. In software and cloud, sustainability often means integrating verification and configuration evaluation into normal delivery flow so evidence remains current. In hardware, sustainability often means maintaining baselines, controlling updates, and periodically revalidating integrity rather than assuming initial purchase guarantees forever. The exam tends to reward approaches that can actually be executed repeatedly, because repeated evidence is what keeps assurance real as systems evolve. Selecting methods that fit organizational capability while still meeting claim strength is an essential engineering judgment. As we close, remember that selecting assurance methods is fundamentally about choosing how you will build and maintain justified confidence, and that choice must fit the system's type, its risks, and its rate of change. Software assurance emphasizes repeatable evidence of correct security behavior and consistent enforcement through change. Hardware assurance emphasizes trusted platform integrity, physical exposure management, and lifecycle control of firmware and configuration state. Virtual assurance emphasizes isolation validity, control plane governance, and drift-resistant configuration evidence. Cloud assurance emphasizes shared responsibility clarity, disciplined configuration and identity governance, and continuous evidence through monitoring and measurement tied directly to requirements. The strongest approach does not rely on one method in isolation, because assurance is layered, intent is reviewed, behavior is tested, and reality is monitored. When you can look at a scenario, identify the security claims being made, and choose methods that produce relevant, repeatable evidence for the most likely failure modes, you are practicing the kind of security engineering reasoning ISSEP is designed to assess. That is how assurance becomes a practical discipline instead of a vague promise.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.